So hello everyone. So welcome to our this week Rogers Efficient AI seminar. And today we're very glad to have Professor Romit Maulik from the Argonne National Lab and Pennsylvania State University to give us this talk. And Romit is the incoming assistant professor in information science and technology at Pennsylvania State University. In addition, he is assistant computational scientist at the Argonne National Lab in the mathematics and computer science division, and he was previously the Margaret Bullitt postdoctoral fellow at Argonne after obtaining a PhD in mechanical and aerospace engineering at Oklahoma State University. And his research interest lies at the intersection of the data science, applied mathematics, and high performance computing. And today, he will give a very, very interesting talk as the neural architecture search for scientific and machine learning with quantified uncertainty. So, Romit, it's your turn.
Okay, thank you so much, Bo, for the introduction, and thank you to all the members of the audience. I appreciate your presence here. I'm sure you've got a bit of the virtual seminar fatigue by now over the last 3 years, but I appreciate that you're still committed to listening to me speak. Feel free to interrupt me at any time. If you have any question, happy to go into any detail that you think you may have sort of not captured perfectly. So, okay, so this is joint work with the broader team that oversees the Deep Hyper project, and I'll go into what the Deep Hyper project is in a bit. So this is a project that is underway at Argonne with Romain Aguel, who is now a PhD student at the University of Paris-Saclay, Krishnan Raghavan, who is also an assistant staff scientist in my division, and Prasanna Balaprakash, who is a senior scientist at Argonne as of the end of this week before he moves to Oak Ridge as the director of AI. So that was a bit of a shock for us, but we're very happy for him. But we'll all obviously keep working together. So thank you again for the lovely invitation, and I'm really looking forward to speaking. Okay, so let's get started. So so the motivation for a lot of the work that I'll be speaking about today, I don't have to convince you. I'm preaching to the choir over here. Machine learning methods have, there's been an explosion of results, workshops, funding, what have you for how machine learning can be applicable to so many science domains. Computational science is not immune to this, and there is this new field called scientific machine learning, which is in my title, where we basically look at classical problems in computational science and computational physics and see how these modern data science algorithms can sort of improve outcomes in these sort of classic problems. So my background is one of essentially numerical methods person. I got a PhD in engineering, but I did a lot of work in essentially numerical methods for partial differential equation solutions. And so some of the problems that ML has sort of become very, very interesting for recently include things like surrogate modeling, closure modeling, signal recovery, so solving inverse problems, generating hypotheses, generating possible solutions for a lot of systems which have classically been required, large high performance computing infrastructure and the solutions of PDEs. So the motivation is quite strong. However, this is a limitation that I definitely experienced when I was a graduate student. And I'm sure grad students continue to experience now, when people, especially your PI, asks you to do like a machine learning or a deep learning type of project, the end result is something that is very impressive, right? You look at these papers and you look at these sort of flagship results in the field. But what is not captured is really how difficult it is to get this, for example, this machine learning workflow into place. Of course, there is a bottleneck in actually developing an algorithm, right? That requires mathematical chops, obviously. But beyond that, generally these ML algorithms can be quite difficult to optimize. So what am I talking about? For example, the hyperparameters of your neural network, or the architectures of your neural network, if it's a neural network, or if there are other algorithms out there. And these are rarely ever reported in any sort of final documentation. Generally, they consider the speed up with respect to like a classical workflow, which in our case is generally a large PD solve, and of course those numbers look great, but we recognize this limitation. And so in this talk, I'll be talking about how automatic SciML, or basically using machine learning for machine learning, can be used to automate this process of optimal, say, hypothesis discovery, right? How do you come up with a nice neural network to do your learning without actually having to spend this sort of time iterating again and again? So this is the motivation. And this leads me to the outline of the talk today. We'll be introducing very briefly this outer loop intelligence that I introduced. Like, so what approaches can be used actually to automate the ML pipeline development process, or to automate the algorithm construction process. And we'll achieve this using DeepHyper, the project I just mentioned. Secondly, we'll see how this process really becomes is scalable and can be used to solve some really nice large practical problems, provided you have access to large computational resources, which again, as a national lab, or as a result of having access to a computing facility at a national lab, we have this capability. Then we'll talk about some applications. We'll go back to the computational physics applications related to forecasting and say inverse problems such as signal recovery. And finally, before concluding, we'll also talk about how it's important for us to. Was there a question? Sorry. We'll also look at how this method can be used to quantify the uncertainty in our prediction. So a lot of these machine learning methods give us point estimates, and these point estimates frequently, since they're coming from a black box, for lack of a better word, can be difficult to trust or difficult to implement into an existing computational workflow without this notion of interpretability. So we'll also see how we can start making inroads into addressing that problem with our formulation. Okay, so let's get started. So very briefly, I wanted to introduce what the DeepHyper project is. So DeepHyper is available online on GitHub at the link that you can see over here. As the name suggests, it's it's like a scalable asynchronous package for hyperparameter and neural architecture search. It has primarily been applied to neural networks, and in fact, it was actually started up as a neural network hyperparameter and neural architecture discovery tool, but now it's grown a lot more, and you can actually do a more thorough version of automatic machine learning, where there are more algorithms that you could possibly search over rather than just neural networks. So, and this has been applied to several applications. I come from a dynamical systems background, so I'll be talking a lot about the surrogate modeling over here for geoscience applications, but at any given time, there are people working on using this for coming up with better machine learning algorithms for cancer drug response, for neuromorphic computing optimization, hardware optimization, for building models for nuclear physics applications. So of course, I cannot speak too much about these other ones, but I can talk a little bit about how it's been quite neat for dynamical systems, such as surrogate models for time series data, which is what I'm talking about today. Okay, so specifically within DeepHyper, the structure of the code is divided into hyperparameter search, which is rather easy to use, and in addition to that, we have neural architecture search. So these are the two sort of subdivisions. I work mainly with neural architecture search. It's quite fascinating, and also there aren't a lot of publicly available codes that do neural architecture search as against hyperparameter search. The way neural architecture search is achieved in Deep Hyper is by representing a neural network as a directed acyclic graph. So, and any graph has nodes and edges. So at each node on a graph, you specify a list of possible operations that become choices, right? And these choices, as you might be guessing, are then sampled by some outer loop intelligence, right? So for example, you could go to a node on this graph and say, okay, add a certain type of layer, or add a certain type of layer with a certain number of hidden neurons, or do nothing is also an option. So just have an identity layer. Add a type of regularization, add a skip connection. So these these 5 options are in some sense the user defined choices. But instead of explicitly specifying what this operation should be, you can let it basically vary. You can also define a node to be a constant. So if you know for sure that a certain node is not mutable, this usually happens with your output node and your input node, because you know the size of your data. You can specify that. But the real flexibility comes from these variable nodes, which are iterated over and then tested and trained and tested to see if it's a good architecture or not, right? But what ends up happening as a result of specifying these operations is that you essentially get a list of choices, right? A list of an array of choices. Each choice corresponds to a variable node. And you can actually interpret this array of choices as something like a phenotype or a gene of a sample from this search space, right? So for example, a search space might look like this, where you specified your input node and your output node by a desired fixed constant node, because you know the nature of your input and output data. You've gone in there and you've then specified these variable nodes, which are given by these blue ovals. And these variable nodes could have many operations over here. The ID could be like an identity operation. You could say, I want an LSTM cell over here. You could say, I don't want an LSTM cell. I just want a regular feed-forward network. You could also have these dotted lines, which mean that at each node, you could say that I want a skip connection from the input or the previous node, potentially, which could be selected as an active skip connection or not. So as you can see, this search space gets sampling from the search space it gives you very, very different types of architectures. I'll show you some examples in a bit. And specifically, another thing is that the size of the search space becomes very, very large, right? So it's actually quite expressive. And I alluded to how you can actually set up the choices from these nodes as a list of a list of choices, and represent this as a gene. You can then obviously use any evolutionary search procedure to initially sample randomly from this graph, and then based on the goodness of these samples, you could then perform an evolutionary sort of optimization to get better and better samples, right? So the final algorithms we end up using are a little more complex than this, but this should give you a sort of a good high-level picture of how neural architecture search works. Okay. What's really nice about this particular approach is that constructing the space is quite simple. If you go through the tutorials that we have liberally provided on our GitHub web pages, you can see that all you need to construct a search space, that I show over here, is a few 20-odd lines of code, where you essentially just specify levels of this graph. So the first level is the input, the second level is these choices, and the third level is these choices, and the fourth level is the output, and provide you can define a variable node. You can add operations to this variable node, which could be LSTM operations, and you can connect a previous node to the next node, and also add potential connections from previous nodes to next node. So you can add potential skip connections. So that's essentially how it works. But what's nice about this is that from the same search space, such as the one that I showed you here, if you just go into the DeepHyper API and then generate some random choices using a random integer sampler from Python, you can see a remarkable diversity in the possible choices that emerge from this search space. So of course, these architectures are not meant for us to examine very carefully or very scientifically. These are just random generations. But you can see on the left, going from left to right, you have, I believe this architecture had around, these two architectures had around order of 100,000 trainable parameters, whereas this one had about 1 million trainable parameters. Again, same search space, just different choices, right? And very, very complex, as you can see. So this is nice. So it lets us have a significant amount of wiggle room in terms of how complex our function approximation task is. All right. So as you can, as you might be, sort of guessing at this moment, if you do have access to, a framework like I just mentioned, where you can generate different architectures from the search space, you could obviously think about assigning these to different nodes that are available in your large facility. And then you could also train these in parallel, right? So let's say you generate 100 initial sort of samples for samples here means neural architectures. You generate 100 random neural architectures. You train all of them by looking at some training and validation data. And the reward that comes to you is the validation goodness of fit. You could then use this reward in a sort of like a rolling window fashion to initialize new architectures that can be fed back into your computing sort of infrastructure as and when resources become available. So and this is a nice setting for using, say, an outer loop intelligence to not randomly keep randomly sampling new architectures, but to actually look at how good an architecture was incorporated into a like a optimization process to sample better and better architectures, and then initialize these better architectures for training and validation. So this is the final algorithm. I don't want to go into a lot of details, but in our final algorithm, not only do we sample new architectures like I just mentioned, but we also sample new hyperparameters, so that you can also as a superset of choices on top of the neural architecture choices that I just introduced. You can also select, for example, 4 possibilities for the learning rate, 5 possibilities for the batch sizes, so you can see the search space grows even more, even though the architecture search space stays constant. And you could combine this into an algorithm which basically lets you generate, as you can say, in a non-blocking manner, better and better architectures. So this is the high-level philosophy of how DeepHyper works. If we have to discuss specifically, for example, the logic used for how the evolutionary algorithm works, as you can imagine, it uses mutation and crossovers, your typical ideas for non-gradient based algorithms. The approach is that if you have a list of choices that currently has the best performance, that is a parent, that is a desirable parent, and then let's say you have some poor performers. The poor performers are removed from your catalog, and these new performers are that replace the poor performers are sort of descendants of the best performers. So that is obtained by, say, randomly flipping the choice of one of the nodes or a couple of the nodes. So these are hyperparameters, but in general, we have seen that our performance is robust to the choice of how we get descendants in our search space. So happy to discuss this in more detail, because I wanted to just give a big high-level overview of this approach. Okay, if I go to the next slide. Okay, so let's now look at a few applications, right? So we'll look at a few applications, then we'll go back to a few more methodological sort of discussions, because the application in many cases motivates the methodology. So in this particular talk, we'll be looking at forecasting the sea surface temperature, and then the sea surface temperature in this case is not something that is it's not, I should say, super difficult to build a forecast model for the sea surface temperature, but it is difficult to build a good forecast model for the sea surface temperature. This is perhaps a first step before trying to build something like a very complex full emulator for a lot of variables in the Earth system. So what we have over here is data that is publicly available at a NOAA repository. It's data that is collected by satellites and ship observations from 1979 to the present day, resolved weekly. So the data is available on a daily basis, but we averaged to obtain a weekly averaged sea surface temperature. And our goal is to make forecasts of the sea surface temperature. The specific forecast question is that given 2 months of observations about the weekly average for the global sea surface temperature, can you predict the next 2 months? So it kind of starts addressing not really a weather type forecast and not really a climate type forecast. That's kind of like a sub-seasonal type of forecast problem, which is of great interest to the Department of Energy. Okay, so as you can imagine, we are trying to build a forecast model for this, but we're trying to actually learn the forecast model architecture using DeepHyper, correct? Okay, so before we go into starting our neural architecture search, I wanted to give a little bit of background about how we make at least for this particular study, the search problem a little inexpensive, so that we can have a good diversity of architectures. And we are working on other approaches, which I'll mention shortly. But when we started doing this work in 2020, what we wanted to do was essentially reduce the dimensionality of our data set so that our architectures could train faster, and would also, if they train faster, you can also imagine we can sample the search space much more widely. And one way to reduce the dimensionality of our architecture is to use basically something like principal components to reduce the dimensionality of our full field. Depending on which community you're in, this has a different name: empirical orthogonal functions, proper orthogonal decomposition, principal components. There are many different names for this, but the idea is that given snapshots of your data, you perform a singular value decomposition of your snapshots, and the singular vectors that you obtain, the left singular vectors, the U in your U epsilon V transpose, can actually are a nice set of orthonormal basis for representing your data in an ordered variance manner. So for example, here is a image that I've repurposed from the citation did not show up, but this is from Tyra and all in a review in the AIAA journal, where there is a direct numerical simulation of flow around this inclined flat plate. And if you collect snapshots of this and perform this sort of modal decomposition and obtain these structures from the left singular, the columns of the left singular vectors in the SVD, you can project the data set onto these two sets of modes. These are orthonormal, and obtain a reconstruction in just 2 degrees of freedom of this original data set with a high degree of accuracy. So we don't have this luxury over here because we're looking at noisy real world data, but we are able to reduce the dimensionality of the problem from 180 by 360 to something to around order of 10 degrees of freedom. So that is one way we can actually accelerate our search process. The other thing is we wanted to use this this approach that was quite popular at the time and still remains popular for doing surrogate modeling in the dynamical systems community. This is called the pod LSTM approach. So you perform a proper orthogonal decomposition to obtain a low-dimensional representation of your data set. So images of your data set become time series in the lower dimensions, and then you use an LSTM to actually forecast the coordinates or the evolution of the state in this low-dimensional representation. And for this, we looked at an LSTM architecture. The LSTM architecture is nice because, believe it or not, it shares a lot of overlap with how one might do a backward Euler discretization of a system of equations. If you basically start with a system of ODEs and you do backward Euler discretization that you were taught in Intro to numerical methods, and you make some assumptions as to how the right-hand side of the systems looks like, this type of set of equations will actually fall out. So that was a nice surprise. But essentially, as I alluded to at the beginning, constructing this type of neural network in the sense of how many hidden layers there should be, how many LSTM cells there should we stack up, what is the dimension of the number of neurons, what regularization to use is not trivial, right? It requires a lot of iteration. We would like to sort of bypass that. Okay. So let's say another reason why we actually use the low dimensional version of this data set was actually at that time we used Theta and not Theta GPU. Theta GPU was not active then, so Argonne didn't actually have access to GPU machines, or at least we did not in this project. We were using 128 nodes of Theta, the KNL nodes of Theta. So we really couldn't afford to run a model that had large CNN candidates. But we have more recently run convolutional neural network architecture, so similar type of forecasting tasks. The search framework itself is agnostic to the type of neural network layer, as long as your neural network layer is expressible in a tf.keras subclass. So if it's compatible with TensorFlow, DeepHyper can search around it. Okay, so this was in some sense the type of neural network architecture that was discovered for this forecasting task. As you can see, it chained 3 LSTM units together, but in between it acquired a bunch of different skip connections, and so again, something that was definitely not easy to come up with manually. Another thing that was interesting is that we at that time in 2020 we were also comparing different algorithms for this outer loop intelligence. I of course introduced the evolutionary approach, but we were also looking at how reinforcement learning may provide results. So reinforcement learning is essentially you would sample an architecture, put it into a training and testing sort of catalog, and then based on how good the validation metric was, you basically go back and sample a new architecture. So this is a good fit for also reinforcement learning algorithm. What we realized is that the evolutionary algorithms, which I just explained, converge much faster than the RL algorithms. The RL algorithms were prone to exploring a little too much, and so we kind of at this moment in DeepHyper, I don't know if the RL algorithms there may be grandfathered in, but the evolutionary algorithm is the one that is most widely used. And so, but both these methods, since they are intelligent in some sense, you can see end up outperforming the random search quite, as you'd expect. The random search starts with random samples from the search space, and of course, some of these samples may be better than the others, but because it's sampling the search space in a manner that is not very intelligent, it doesn't really get that extra sort of 5 to 6% of performance that may be crucial for your SciML application. Okay. All right. So as usual, when we submitted this to SC, the reviewers came back and said, "Oh, how repeatable is your study?" So we kind of reran the evolutionary algorithm approach, I believe 10 times, and was it 10 or 20? I don't remember. I think it was 10 times. And we computed how the validation R-squared looks like. And as you can see, in general, the trend of early convergence is seen, as we saw it in our first run. So that is that was nice. Specifically, if we also, back then we also wanted to compare how we were performing against reinforcement learning. And one thing we noticed was that in terms of both, well, you already saw how things look like when it comes to the metric, the reward metric, but in terms of node utilization, as in at any given point of time, how many nodes are actively training, our reinforcement learning algorithm was much lower than the evolutionary algorithm. So you may be wondering why I have these confidence intervals greater than 1 here. That is just a like an artifact. We were computing the standard deviation and we added and subtracted. So the standard deviation does not mean that we had greater than 1 node utilization. It means that there was a big variance. But in general, you can see that this trend is higher than that of the RL. So that is another reason why, as you imagine, keeping half the machine empty in the process of doing this outer loop intelligence is definitely not going to make the LCF people very happy. So that's why it's been abandoned to some extent. Another sort of representative result comparing the reinforcement learning and the so you may be wondering, why am I looking at reinforcement learning so much after not talking about it? Because back in 2019 and 2020, there was a significant amount of literature and actually using reinforcement learning for this type of neural architecture search. It's still around, but we wanted to see when we are talking parallel reinforcement or parallel neural architecture search, the inherent bottlenecks with parallelized reinforcement learning, right? The fact that you have to capture a batch of evaluations before you can aggregate gradients and improve the agent that's sampling, it kind of is fundamentally ill-suited to the high node utilization requirements of, say, LCFs. And when we performed some these typical sort of studies for how as we increase the number of nodes that we are searching across, that we want to see how the number of unique architectures. So that was our metric for a good search. We wanted to see that how many unique architectures we had over a certain goodness of fit. These were going up much faster for the evolutionary algorithm versus the reinforcement learning algorithm. And as you can see, the random search, as expected, does not really go up. So that was nice. And you may also be wondering at this moment, okay, that's all great, but how did it perform against your let's say graduate student descent, right? If you put a grad student to work on this for 1 day, how would they come up with something that's competitive? I wasn't a grad student at this time, but I spent a couple of days trying to manually come up with an architecture that could beat the performance of this search, and I really tried, as you can see from the table over here, but it was difficult for us to basically match. We were match the performance of the search space. The search space was always 5 to 6 percentage points more accurate in both training and testing. So of course, this doesn't mean that there might be someone with the magic fingers out there who could sit at the laptop or on his workstation, his or her workstation, and then come up with an architecture that is superior to what we discovered. It's always possible, but we would rather they spend their time on more valuable things. So and we also compared, of course, against linear methods and tree-based methods, and the standard benchmark comparison showed us that we were doing better. So that was a good validation. In terms of the science, if we go in there and we looked at how we actually performed, So, in comparison with state-of-the-art weather and climate forecast models. So, there are, the sea surface temperature is predicted by a bunch of partial differential equation-based models, which also compute many other things. When we looked at the root mean squared error, which again is one metric, it's not the only metric. We saw that we obtained competitive results, even though the table here seems to suggest that we outperformed CSM, which is a climate model, and HICOM, which is a Department of Defense weather model. There are too many sort of uncertainties over here in terms of the grids people have used, in terms of the formulations people have used, to make any claim other than the fact that we are competitive. And especially if you think about how cheap it is to evaluate our, I have numbers specifically in 2 slides, but as you can see, we have a surrogate at the end of the day, right? We have a neural network rather than a PD. So we are actually able to, provide a nice sort of alternative to these other methods, which are essentially extremely expensive to run. So, and the reason why I say we are a complement to these equation-based methods rather than a replacement for them is that based on the method you choose, right? So we are maximizing a metric based on our neural network, learning process. You could choose different points in your flow field. In our case, the sea surface temperature, where again, to the naked eye, you could get results which may point in favor of one method or the other, right? So as a bulk metric, yes, we do better, but there may be regions where one is better than the other, right? So we definitely do not want to say that throw those things out. Ours is better, which is not our intention at all. But what our intention is that if, for example, you compare the cost to run these other methods. So for example, HICOM, which is a weather model, requires 800 core hours per day. At least this is the only documentation I could find online. On a Cray XC40, and we are making forecasts for 2 weeks. And weather models, by the way, don't even make forecasts for weeks. They basically blow up much sooner than that. So it's kind of not really an apples to apples comparison, but let's assume that we were running this forecast for 2 weeks using HICOM. So that's 800 core hours per day. So you can multiply that by 14 to see how much resources you need. CSM, of course, is a massive climate simulation that doesn't just provide sea surface temperature, it provides many more other things. And as you can see, it's 17 million core hours times 30 members. So yeah, again, not a fair comparison at all, because you get a lot more out of CSM than just the sea surface temperature. But just to give you an example, by bypassing the solution of a set of PDs, you can come up with something that is basically click and see. So we required 180 node hours of theta. So sorry, 128 into 3 node hours of theta. So yeah, you can do the math. It's around 500 node hours of theta, and 400 node hours of theta, and we are able to come up with something that could potentially be used as a boundary condition to one of these equation-based models, or could be used for rapid data simulation, right? So you could come up with initial conditions by using this forward model that could be then fed into an equation-based method. So there's many possibilities for how you might want to use these surrogates. So that's why this is a complementary approach. So anyways, this study was published in SC20, and it's available at this link. So feel free to go give it a look, and let me know, or let us know if you're interested, or if you have any questions. Okay, so moving on. So I don't know why the resolution of my pictures looks so bad on Zoom. It looks better on my laptop. Anyway, so what we wanted to do beyond this is, of course, we have this approach to finding the best model, but the best model, again, is a point estimate. And so an easy extension of our work that really improved sort of the attractiveness of this approach was to not simply use the best model, but to use a bunch of high performing models for our forecasts, right? In essence, that was what we went for. And we were motivated by this by looking at a paper from Google in 2017, which introduced what's now known as the deep ensembles approach. The deep ensembles approach back then in 2017, 6 years ago, said that instead of training one model with your data and then using it as a point prediction, you could train a series of models. I believe they used an ensemble of 10, and then come up with an ensemble of predictions, which would give you, of course, confidence intervals, right? So we'll go into the math in a little bit. But what they proved was that this approach was actually superior to other typical methods for providing predictions with uncertainty quantification, such as your Bayesian neural networks or Monte Carlo based dropout or probabilistic backpropagation. And we thought over here that we already have a philosophy that searches for the best weights, searches for the best hyperparameters, and also now with neural architecture search, we also search for the best topology. Why not, instead of selecting just for the best topology and the best hyperparameters and the best weights, we sample from high-performing combinations of these three, and then obtain a series of ensembles from our search, which can be used for uncertainty quantification. So in terms of what additions we had to make in our search space to actually perform uncertainty quantification, well, there are two types of uncertainty in any sort of functional approximation. There is the epistemic uncertainty and there is the aleatoric uncertainty. And these words have and continue to confuse me in conversations, but basically the epistemic uncertainty means the uncertainty in the model, and the aleatoric uncertainty is the uncertainty in the data. So the uncertainty in the data is not reducible. That's a function of your training data, right? You can only reduce it by getting more data from your from your physical process. To account for your epistemic uncertainty, you can simply use different models, right? Just choose different models and average them. That is how you get, and find the variance. That is how you get the model form uncertainty, because there are different models which are slightly different. For your aleatoric uncertainty, for your data uncertainty, you need to have a model output that can predict the hyperparameters of your distribution. So rather than having a neural network that just predicts Y from an X, you predict a distribution that Y may be sampled from. So you predict the mean of, in this case, a unimodal Gaussian and a variance, and then you can basically change these values given the input, right? So for example, for one input, you may have a neural net that comes and predicts this type of behavior. For another input, you might get this type of behavior. But the same net input, if you have different models, you can get different types of behavior. So it really increases the flexibility of our our approach in terms of capturing these distributions for the output, right? And so the overall approach is shown on the right-hand side. This is just a repeat of the algorithm that I had early on. You basically have an intelligence, as you see on the left-hand side. It samples the search space. The search space trains on some training data and computes a reward on validation data. This reward is then sent back to this intelligence, which is the evolutionary optimization. At convergence, instead of taking a point estimate, one model, you construct a catalog of the highest performing models. And actually, there are different ways to construct this catalog as well. It's not merely choosing the top, say, K best ones, but that's what I'll be talking about. You can then find a mean prediction from these models. So for each data point, you get, say, in this case, there are 4 models, right? You get 4 predictions for each data point. You can average the 4 predictions to get a mean. You can get a variance from the 4 predictions. The variance can be decomposed into a model form as well as a data uncertainty. And this decomposition follows what is called the law of decomposition of variance. So when we go ahead and actually perform this for some benchmark problems, so these are benchmark UQ problems in the machine learning community for regression. Of course, we have to provide these when we are talking about pitching something to the machine learning community. So we performed extensive comparisons with different methods such as probabilistic backpropagation, Monte Carlo dropout, deep ensembles, which is the original paper in 2017, where they did not change the hyperparameters of the architecture. They just did repeated trainings. And as you can see, we were able to, in general, outperform a lot of these other state-of-the-art methods quite nicely just by relaxing the fact that, or by discarding the fact that each architecture has to be the same, right? You can have different architectures, different hyperparameters, and so on. We were able to improve on them. So this was nice, and this benchmark paper, in which we haven't looked at dynamical systems, we've just looked at benchmark regression problems, is available at this link over here. Also, if you are interested, please take a look. But we'll go back to our problem over here. So we wanted to do this forecast that I talked about, but specifically we wanted to now quantify the uncertainty in our predictions. So if we construct an ensemble again of, let's say, 10 members, but in principle, if you have a large computing infrastructure, you could now start really looking at large members of ensembles, which is nice. And we were able to see that, well, firstly, that the uncertainty of this particular model is concentrated around the coastal regions, which is not surprising. This is also what like PD-based models tend to demonstrate because of the interactions with the shores. The epistemic uncertainty dominated the aleatoric uncertainty, so the model form uncertainty was more severe. And of course, the error that we got over here, we noticed that the uncertainties near the coast were correlated with the errors, with the exception of ENSO, which is very difficult to pick up in an 8-week sort of signal. So this error on the west coast of South America, the seasonal oscillation. So that means that we can build better models, essentially, right? So but still, this is a nice feature of our model discovery paradigm. What is more interesting is when we actually looked at the comparison of the prediction from the ensemble versus the prediction from the individual members. So the 10 members that we chose for the ensemble were all very high performing. One of them is one I showed you results from. And so what we did was we just binned the root mean squared errors. So we created histograms of the root mean squared errors for the individual ensemble members as well as the ensemble. And when we subtracted these sets of histograms, we saw that the ensemble has a density for root mean squared error, which is much higher, closer to 0, which means that its root mean squared error density is closer to 0, like the mass, the density. So it's predicting errors which are generally closer to 0 in comparison with individual ensemble members, right? And in a more quantitative sense, when we looked at the assessment I showed you from the SC20 paper, which is the bottom 3 rows over here, when we looked at the ensemble prediction, the ensemble mean, we were able to get a much lower root mean squared error than our previous approach, which was just selecting one good member rather than constructing an ensemble. And this is not surprising, right? So as long as you're exposing the same training data to each ensemble member, the biases that may be present in individual members will basically be sort of corrected in the ensemble. So this was a nice result as well. So we're getting a little more out of our neural architecture search now. So this work was out on the archive actually very early this year. So it's still under review, but feel free to take a look to see what you think. Okay, so going ahead, I have one more problem, which is not very important. I think your questions are more important, but over here we looked at, instead of the forecasting problem, we looked at a sea surface temperature recovery problem. So given sensors at these locations on the surface of the Earth, can you reconstruct the entire flow field this was not an LSTM, like a forecasting problem. This was like a fully connected neural network. So we just go to the entire 360 by 180 field. This is how the search space looks like. Initially, you have a little bit of exploration for one search, but then you basically converge quite quickly. I'm just going to go through this quickly. You also get estimates of epistemic and aleatoric uncertainty. So in this particular data set, we were able to actually have high correlation between the aleatoric uncertainty and the ENSO, which means that our model was actually constructed well. The training data was adequately chosen. So and I have 5 minutes left, but I will just conclude by saying that there are still a series of limitations that we need to address in this particular problem. One of these limitations is that each ensemble member at the moment assumes or it requires requires the entire training data set, because each ensemble member is considered perfectly equal to the other. So, but in practical problems, your training data is going to be difficult to fit into one GPU or even on one node. So we are actually investigating at this moment how we can construct these ensemble methods where each member of the ensemble is more significantly biased because it's seen only a partition of the total data, right? So the problem then converts from being a model ensemble question to a model aggregation question. So how do you aggregate these models rather than just average them, right? Of course, we are always ever interested in looking at more complex neural architectures. The search continues to get more and more off-nominal, so to speak. So that is something that we are always looking into. And finally, we would also like to implement these as I'm sure you're familiar, these physics constrained ideas into our search. At this moment, our approach is purely data driven, right? But given that we have some intuition about our process, in my case, the dynamics, or that we have some intuition about what equations may be driving these data sets, can we actually implement them into our search as a searchable layer? So can we search for constraints in addition to searching for the forward model, right? That would be very, very interesting, because it would start addressing the issue of scientific discovery rather than just just accelerating computational science, right? So that is something that we are very interested in. Okay, so I think that was the last slide. So thank you again very much for the invitation. It was a pleasure to speak here. Some acknowledgements up here that supported this work. And I'm happy to take any questions or any comments. Thank you.
Thank you, Romit. Very interesting presentations. And any questions from our audience? You can unmute yourself.
Hello, Romit.
Hello.
My name is Wen Chen. I'm an assistant professor from Florida International University. And I also did some work to design neural network models for ocean modeling, like the figures you just showed me.
Okay.
And I'm also considering using the ensembling. From your presentation, let me double check it first. You construct a basic neural network model based on deep hyper, and then construct an ensemble model to improve the accuracy, but you may need more computation resources to build the ensemble model. Am I correct?
So we do not construct a baseline. We just give this neural architecture search all our data, and it searches for good models. So what we give it is essentially like a search space. So let me show you the exact slide. So for example, over here, we will say, let the input be, like the initial condition, let the output be, the prediction at a certain time step, if you're talking about forecasting, and then we give our search space to this deep hyper. The search space has multiple options for modeling choices, correct? So it will make a choice, it will train that model, right? If that model is good, it will remember that and make another choice. If it's bad, it will remember that and make another choice. I'm simplifying, but essentially that is the overall logic, right? So we don't make a first model and then improve it. We just show the data, we give the space, and then it searches the space for better and better models.
So based on this graph, I have two questions. How can we define the search space? Like here you're using multiple LSTMs and
Yes.
connecting with some dense models, some dense layers. How can we define this? And
So that's a good question. So over here, the only choices that we had to make were these blue circles. So we said that there are you see these italic ends over here. These are the choices that the human has to provide. The human just says that N1 could be a bunch of LSTM cells, N2 could be a skip connection or not a skip connection. Similarly, N4, N5, N3 would be just choice of LSTM cells. So it's not that the human just sits back and relaxes. Okay, there has to be an initial sort of stage where we have to go with some intuition to construct this search space. But it's a lot easier than constructing the specific architecture. So over here, when we are doing forecasting, this search space requires sequential data. So that's why we chose LSTMs, right? So when I was constructing the search space, I just said, okay, let me just have 5 variable nodes, and let me put choices of LSTMs at these nodes, and let me allow skip connections between nodes. That's the only thing I had to put in there. So,
okay.
So I did not have to go in there and say, okay, let this be an LSTM of this much, width, let that be a skip connection, let this be a dense connection. So these dense layers are automatically discovered by Deep Hyper, because in order to connect the input to this LSTM, it has to do a shape change, right? I mean, if the input is say 100-dimensional, but this LSTM requires a 10-dimensional input, then there has to be a matrix vector multiplication over here. So it discovers that. So we don't have to do that, but we have to prescribe some guideline for the search.
I see, which means we need to provide some empirical experience on this.
Of course. So if we, you need to know your, machine learning 101, so to speak. If it's sequential data, you should not give it a fully connected network. If it's, if you're looking for advection dominated problems, such as, ones where you have shocks or something, then it's better to give it, like vision type architectures with convolutional layers, because they are good at capturing like local features which move and so on and so forth. So some basic intuition is required, but then the process of optimal architecture discovery can be automated. Yes.
And can I, based on this graph, can I recognize it as a modular neural network? Because it looks like some of the components can be taken as a module, and
I'm not familiar with that terminology. I'm not familiar with the modular neural network terminology, so I my answer is I don't know. But
no worries. Probably we can discuss this offline and see.
Sure.
Yeah. Okay.
So, yeah, thanks for the question. Yeah, it was very interesting.
Thank you so much.
Other questions from our audience? Yeah,
feel free to email me, anyone, if for example, you need to ask anything detailed, I'm also happy to meet. I can also share these slides with you if you're interested.
If no question from audience, actually I have several questions.
Okay, great,
Yeah.
excellent.
And the first is about the search method. So here in your presentation you mentioned that you use the evolutionary based method and also the reinforcement learning based method. So I was wondering, whether you have tried those the differentiable based NAS method.
Like a differentiable based method?
Yeah, differentiable based, for example, use the Gumbel Soft Max based differentiable NAS. Yeah.
No, we have not. So the short answer is no, we have not looked at differentiable based methods. And honestly, I do not have a lot of experience with differential based NAS. So we just found that the evolutionary approach was such a good fit for our asynchronous type of learning that we kind of haven't really explored differential techniques after that. But yeah, I mean, thanks for the note. I might go back and take a look at it. It sounds interesting, yeah. But no, short answer is no, we haven't. Yeah.
And another question is about the search cost. So how about we know that the NAS is kind of one potential drawback is that in many cases that it takes a lot of the search time. And
yes.
I was wondering, so yeah, for your work, how about the search cost? How many GPU hours and so on?
Sure. So the first part of the talk where I was, let me find. So when I was doing this search, if I can find it, this was essentially 3 hours on 128 KNLs. So this is a smaller problem, right? So this was 128 times 3 node hours for KNL. The second part of the cost where I recreated this problem was a second part of the talk where I recreated this problem. We looked at 2 GPU hours of 2 hours on 64 GPUs. So we're looking at 128 GPU hours for this convergence. Convergence happens earlier, as you can see, but we still let it run for discovery. And this is exactly what I alluded to in the final slide, right? When we have a data set that is almost impossible to train multiple samples of, right? We have to go to the max. And the math is basically telling us that we can train in a federated manner. That's fine. We can train on partitions of the data. How do we unite these partitions and kind of still use it for NAS or still use it for model ensembling or model aggregation, right? So that's kind of like an unsolved problem we are very interested in.
Yeah. And another question is about the search component. So here, like in your search space, you consider the dense layers, the LSTM layers, and so on. So, and I remember in one of your slides, you mentioned that the LSTM, so surprisingly, it shares kind of similarity with the OD equations and so on. And we know that in the neural work models, in addition to LSTM, the emerging transformers, they're also kind of naturally suitable for capturing the sequential correlations and so on. So I was wondering, have you considered that to extend your work to cover to include the attention layers in your search space?
So there's a funny story there. This is not published work, but when we actually expanded our search space to include transformers, we can do that because as long as your operation is a TensorFlow Keras layer, you can search across it using REFAI. But we ran these searches for transformer based learning, and we were not able to outperform LSTMs because my metric, again, I come from an engineering background, right? My metric is, when I say outperform, I mean outperform comprehensively, right? Not just one model is better than one LSTM. It has to be statistically better, right? So statistically speaking, I could not reject the null hypothesis that both are the same. So, of course, that result is very difficult to publish, right? Because people expect transformer to be better. So, so we kind of have been sitting on it, trying to make sure that, our result is absolutely sensible. But recently there was a paper that was submitted to the archive, where there was a I can share the paper with everyone, but it's not from any of people I know. But they showed that for ordered data, not sequential data, when you think sequences in terms of language, there is some ordering, but also it's open to interpretation, right? So it's more like clumps of context which are together, which is what the attention is a very good fit for. But in time series data, ordering is strict. 1, 2 comes after 1, 3 comes after 2, right? There is no room for interpretation. So in ordered data, the transformers are beaten by linear models. So there's a paper that was out recently, which a lot of us have looked at and are kind of amazed. They set up linear models for time series forecasts, and they said we are beating transformers handily. So because the transformers, they kind of explicit ordering is removed for this sort of like token embedding, right? I mean, they don't have an ordering anymore explicitly. So that makes the learning more difficult, I think, for applications like this. So these are results I also got, but I wasn't sure why we were getting that. I think some people were braver than me and just put it out there. So but short answer, yes, we are interested in like looking at many different types of architectures. Our goal is to drive that error lower and lower, and yeah. So we're also interested in looking at mixtures of types of hypotheses, right? Just not, could be combinations of LSTMs. We're also looking at neural ODEs, neural ordinary differential equations, which are also a family of these RNN type methods. So yeah, so we're trying to make this as flexible as possible.
Thank you. And actually I have some other questions, but first I want to let the audience to ask if they have some other questions.
I have a question.
Oh, hi.
Yeah, hello, Romit. So my question is that regarding this neural architecture search, so how can we, apply this to reduced order modeling? If I'm, let's say I'm trying to make a reduced order model for to the turbulent flow simulation across a cylinder, something like that. And how can I implement this technique to search for better architectures for reduction techniques, like using deep learning, something like that?
So I have done some work internally for this, where we kind of used deep hyper to search for better autoencoders. So you can think of snapshot data. We use POD over here, but you could also bundle that into the architecture search, where we not only learn the evolution in the latent space, we also learn the discovery of the latent space. So you can chain these nodes having different choices for hidden layers, but then you can fix the latent space as a fixed node. So you see, like I don't have a schematic that can really do a good job, but let me see if I can make do with the one I shared here. Let's say that over here, instead of letting this be a variable node, can you see my pointer, Srinivas?
Yes.
Yeah. So here you can specify that this node is fixed at a certain dimension. That dimension is of interest to you for your reduced order model, right? So
yes. Okay.
So it searches around that fixed latent space to obtain a good representation for good output error, like low error in reconstruction. So that could be one way to reduce your dimensionality. And then you can also, you can layer on all sorts of complexity over here, right? In the latent space, you can also add time-dependent behavior.
Yeah.
So yeah, there are many things, but that's us. So this is what, the first question was about intuition, right? So you have this intuition that you want a latent space that is low dimension, right? So you then code it into your search space, and then let the search work around that constraint.
So when it comes to unsteady simulations, and we are using LSTMs here. So in latent space, do we need a separate time dimension, or does that get covered with LSTMs?
So, well, you'd have to sit down and think a little bit about how you want to code this in the API, but it's possible. So you would have, let's say, a search space which consists of, like a non-time dependent element, then a time dependent element in the latent space, and then a non-time dependent element. And then you'd have like a composite loss of both reconstruction as well as time evolution. I haven't done this. It would be a nice sort of project, I guess, but it's possible. Yeah. Of course, the easiest thing to do is you learn your compression separately and you learn your time evolution separately, right? That you can easily do, right? By doing two neural architecture searches, one that builds on top of the other. But if I understand you correctly, you're trying to do everything at once, which is of course going to be a little more difficult, but it's possible. Yes.
Oh, thank you, Romit.
Sure.
Other questions from audience? Because Romit, can I ask the last two questions?
Oh, please go for it. I'm here to stay.
Yeah. And one question is that actually I like one of your slides that shows that from the different scopes, search the weights and search the hyperparameters and search the topology.
Yes,
and
yes.
At the end of your presentation, you mentioned that about the uncertainties, we can use kind of the assemble of the different models together.
Yes.
So I was wondering, whether we can further to extend your framework to kind of become uncertainty aware net search. We can also search the number of the neural works you want to put together to reduce the uncertainty.
Number of networks. Let's see. I'd have to think about it, but we can certainly use some metric of uncertainty to affect our search. So for example, let's say that you want to do uncertainty aware search. So you get validation metric, which is used to sample the search space. You can construct a complex metric, right? You can compute some form of likelihood, some sort of metric for uncertainty based on the members you have in your catalog at the moment, and use that to tell the outer intelligence that this uncertainty has to be reduced, let's say, and then it samples, which I haven't thought about. Thank you for making me think about that. So, but to search for the number of models, what we did was, if we run on sufficiently large machines, we end up having thousands of model candidates. So we save all of them, right, to disk, because these are just model weights. And then in an offline processing step, what we do is we select for the best number of concepts. So instead of selecting just the top 100, we look at, in terms of accuracy, we also use like Caruana type selection, I'm not super familiar with those, but we look like more intelligent ways to subsample the 1000 that we saved. But we don't do it online. We do it offline at the moment, the ensemble construction. But I think using the uncertainty to affect the search is something that is going to be more easier than using the uncertainty to decide how many models to keep online. I don't know. I have to think about it, but definitely we can change the reward metric from accuracy to something more complex. Yes.
Yeah, add some more loss terms that you overall.
Of course, you can actually, in DeepHyper, I didn't talk about this. We can even do multi-objective optimization. We can get Pareto fronts.
Oh. Okay.
Yeah, so we can provide, we have a result on our tutorial pages where actually using my problem. They like using my problem. It has nice pictures, but you basically, you can get a Pareto curve between a Pareto front between accuracy, which is the only thing I showed you, and the number of parameters. So you can also search for cheap surrogates. in addition to accurate ones, because obviously more parameters may lead to more accuracy, right? Generally speaking. So you can get a front which shows that you can reduce the accuracy, but increase the evaluation time, or sorry, reduce the evaluation time because the number of parameters is lower. So that is also possible. So if you specify more objective functions, it'll give you like a Pareto front. So we have like a because we are using genetic algorithms, we can just do the non-dominant.
Yeah, it's naturally suitable for the multi-objective organization.
Exactly. But we can also like do composite objectives. So we can add, like you said, we can add objectives as well. We can come up with arbitrary complex objectives. So it's as a function of neural networks. It's quite straightforward. Yes.
And one last question. Yeah. And so at the end of your presentation, you mentioned that moving forward, so some future directions about the neural ODE. And so we know that like the neural ODE or the physically informed machine learning are very, very hot. And so in the first part of your slides, so you mentioned that your architecture is that we have some it's similar. It has share some similarity with the ODE, but it's still kind of some different. And I believe that use the neural ODEs you can deeper embed the domain knowledge to the architecture.
Oh, absolutely.
So how do you think this kind of this seems like two different type of directions? So how do you vision the potential for the different strategies?
In the context of NAS or generally in the context of machine learning? Like, are you asking in the context of deep hyper, or are you asking like more generally for?
More general for the AI for scientific AI.
Okay.
Yeah, because we know that.
Okay, so I can tell you what my feeling is, but I don't know if it's right or not. But like, I feel the reason a lot of us like neural ODs or things like physics-informed neural networks is that they are not too far from our comfort zone, because we kind of talk about ODs, discretization, about like finite element methods, and in some sense we want to keep those things relevant, right, when we are trying to learn. So honestly, I believe that the best way forward is to have a data-centric approach, which means that based on your application and your data, you may have to discard some of these more inductive biases to get a better performance. But in many applications, maybe these inductive biases give you very nice performance. This is a diplomatic answer on my end, I guess. It's not always going to improve your modeling strategy. To give you an example, recently, I don't know if you've been following these. There is this competition, not competition, but like there are like 3 or 4 groups in the world who are trying to do weather prediction with machine learning. There is NVIDIA with ForecastNet, Microsoft with Climax. There's a group in I think I want to say Baidu, who have their some weather model, and there's another group in Google, GraphCast. So these are 4 who are really competing with each other to give the best weather prediction. And the funny thing is, statistically speaking, they're all giving the same result, statistically speaking, right? I mean, they're all very close to each other. To me, they're not different results, but people say I am 1% better or 1% better. But the funny thing is, all 4 of them have different architectures. Google is using graph neural nets. The Baidu is using transformer. NVIDIA is using Fourier neural operator, which is like a physics-informed approach. And Microsoft is using, what are they using? I forget. Maybe I think they're also using GNN. But so essentially, you're seeing that in this case, it's a data problem. It's not a inductive bias problem. All models are giving similar types of results, no matter what you choose. So yes, for my job security, physics-informed machine learning is good, but I do believe that like based on the problem, you may be benefiting from letting some of those go. You see, so But yeah, so that's the data-centric approach. I mean, based on your requirement, based on your application, on your data, I think you should be flexible.
Data matters. Yeah.
Yes, data matters. Most. I think 95% is data. You will agree with me, right? So all these other things are, cool, but I think if you have bad data, or if you can get more data, it's always a good thing. So
Thank you. Thank you very
Sure.
much. Yeah.
Yeah,
I think we can
absolutely.
discuss more offline. Yeah.
Well, absolutely happy to chat with
Yeah.
anything, and hopefully we run into each other sometime. Thank you very much for the invitation. It was a pleasure.
Thank you very much. Thank you very much for giving us such inspiring presentations and talk. And also thank everyone to attend our this week seminar talk, and see you next Thursday. Okay. Bye-bye.
Thank you, Romit. See you. Bye.
Thank you.
Bye.
Bye.